Okay, and last portion of this, and then I will expect that 10.3 evens that I signed are done and ready to turn in on Friday when I see you. So anyway, but let's look at number 55 because I believe I was having you prove the Cauchy-Schwarz inequality on number 54. So number 54, if you're looking at that on page 860, basically says that the absolute value of a vector dot b vector is less than or equal to the norm of a vector times the norm of b vector, right? Well, I'll give you a hint. This is, what we have a theorem that you need to use, and this theorem says that the cosine of theta is a vector dot b vector over norm of a vector, which is always positive, times norm of b vector, which is always positive. So I don't know, maybe go up here and take the absolute value of both sides. So that's your hint on that one. All right. Anyway, so let's move on to, and by the way, do you know what sine and cosine are bounded by? What the max height and the minimum height would be for those? So I think that'll help prove that inequality. But anyway, so let's go to 55. 55 is saying if a and b are any vectors, then the norm of a vector plus b vector quantity squared is going to equal the norm of a vector squared plus 2a dot b, a vector dot b vector, plus norm of b vector quantity squared. Well, this is kind of neat because when we have a plus b quantity squared, the FOIL becomes the fool, right? And it's a squared plus 2ab plus b squared. So notice this is a one-dimensional version of a multi-dimensional theorem. So that's pretty cool. So we're going to let a vector and b vector be in the same space. Could be 3 space, 2 space, 1 space, which is this one, or in space. But anyway, so let's go ahead and try and prove this out. How are we going to do that? Well, we want to, it gives us a hint on this one, and that's to use theorem 10.3.3, bullet point number 3, which basically says what? It says that a vector dot a vector is the norm of a vector quantity squared, right? Because, and by the way, what's the proof of this? What's the norm of a vector? Well, it's a sub 1 squared plus a sub 2 squared plus all the way to a sub n squared. Square root of all that, but then if you square it, what do you get? You get a1 squared plus a2 squared plus all the way to a sub n squared, which these are the same, right? That's what a vector dot a vector is, because you put them on top of each other, multiply, and then add the results, and both sides are the same. So we're going to utilize that to prove our theorem. So really what I can do is, well, a couple of things here. So you might say, well, could I put that over here? Well, you could, but what I'm going to do instead is I'm going to work with this side and use this theorem. So I can say, let me clear out, give myself some room. And so I'm going to say that the norm of the left side is what I start with, right? And I want to end up with the right side. So I'm going to start with the left side, which is norm of a vector plus b vector quantity squared. By the theorem that we had, that's going to be a vector plus b vector dot a vector plus b vector, right? So that's how I use that theorem. So the norm of a vector squared is a vector dot a vector. So the norm of this thing, a vector plus b vector, that could be, you could call that c vector, if they're in the same space, would be c vector dot c vector. So, but what can I do here? So we do have this from that theorem, 10.3.3, whatever. But anyway, so the question is, what's this equivalent to? Well, what I can do then is I can take this part dot this part, and I have a theorem. So this is equivalent to A vector plus B vector dot the first one in this one, which is A vector. So dot A vector plus the first thing, A vector plus B vector dot the second one, B vector. And what law is that I'm using? This is the this is actually the distributive law that we had for vector dot products. Once again, if you don't see this, if this confuses you, we could just call this C vector here. And if I call that C vector dot A plus B vector, that's equivalent by the distributive law to C vector dot A vector plus C vector dot B vector. So maybe you see that a little bit better. But the C vector is nothing more than this A plus B vector here. So that's what this one is. But anyway, so we have that from the distributive law. Of course, we have the commutative property that you know, A dot B is the same as B dot A, where A and B are vectors. So I could switch these around, but really I could use the distributive law again, and I could say, hey, this is A vector dot A vector. So if I take that dot product and distribute it over that, plus A vector dot B vector. Now you might say, well, wouldn't that be B vector dot A vector? Remember, we have the commutative property as well, so we're probably using that also. Plus, then I can do it again over for this one. I can take that B vector and take that dot product over these. So this is A vector dot B vector plus B vector dot B vector. Okay, so I know what you're thinking. So you're saying, well, this should have been B vector dot A vector. If we're doing that correct, and that's true. So not only am I using the distributive law twice for dot products, but I'm also using the commutative property that says that A vector dot B vector is the same as B vector dot A vector. And why did I do that? Well, now I can combine these two. And remember, A vector dot B vector is a number, so we have the same number plus the same number is 2 times that number. So it's 2 times A vector dot B vector, right? And then, of course, so that's those two. And then what do I have here? What's A vector dot A vector? Well, by that theorem that we had, 10.3.3 theorem, we said that is the norm of A vector quantity squared. And by that same theorem, this is the norm of B vector quantity squared. So we get our very nice multi-dimensional result that looks a lot like the result you have for real numbers when you have A plus B quantity squared. So there you go. That's all I got for today. Should be everything you need. I do know that I will mention that last example is very hard. Example 7 is a very nice geometry example. If you're like me, I don't really like geometry much, but Luke and I spent a lot of time going through that, following all the steps and verifying that. So make sure that your eyes kind of gloss over. There's so many moving parts and steps on that, but try to take some time with that. We spent about probably on that maybe, just stepping through each piece of that to verify what was going on. And so when it's saying which line segments and which vector segments they're looking at, try and follow that as they go, and maybe draw that on the board or something or in your notes, and make sure that you can follow example